Hello everyone, my name is Rebecca Cid from Amura, and before focusing on the adhesive itself, I would like to briefly present the BioStrack project and our use case. The idea is to provide some context for why this solution is being considered in our demonstrator. So first of all, I would like to explain why composites still represent an important challenge today. So there are two main reasons for this. On the one hand, there is still a strong reliance on glass and carbon fiber because approximately 8% of the raw materials are manufactured outside of Europe, mainly in Asia. On the other hand, this material still face major end-of-life limitation, especially in terms of recycling and waste management. So these are the reasons why it's necessary to find more sustainable alternatives. So how do we address this? Is by focusing on biocomposites. So natural fibers such as flax and hemp offer real potential for the development of more sustainable composite solution. And they can also support local value chains in Europe. However, their use in a structural application is still limited, mainly because the behavior of this natural fiber is less consistent than the conventional reinforcements. That is why further work is still needed to better understand the material and adapt both design and process, manufacture and process, of course. Sorry. And it's precisely this need to better understand this behavior of the natural fibers that gave rise to BioStrack. So the project trying to handle this or to address this challenge combines different areas of work, including draping, material modeling, and sensing. And it validates them through two pilot actions. So for one side, CIDETEC is manufacturing a curved wing outer shell for aeroplane, and the second pilot is a motorboat that include the hull, the deck, and structural components. Is the second pilot action that is being developed for us at Amura. We are a company based in Vigo. We are a shipyard and marine services company with experience in mainly boat building, refit, and composite processing. So we are always looking for innovative solutions for the nautical sector, and it's why, or it's the reason why we try to be active in innovation projects such as BioStrack. So in this project, Amura is manufacturing a 6 meters motorboat as a demonstrator. Actually, we already manufacture this model in glass fiber, but during the project, this design has been adapted to work with bio-based composite materials. This gives us the opportunity to evaluate these materials and processes in a real marine application. From a technical point of view, the whole boat is being manufactured using bio-based composite material, including the hull, the deck, and the internal structure. The reinforcements are based mainly on flax, within a hybrid flax basal laminate in the whole structure. The matrix is a bio-based epoxy resin developed within the project also by Noma Resin, a Polish partner. And the selected manufacturing process is vacuum infusion. In addition, this demonstrator will also integrate the reversible adhesive, which is the main solution we want to present today. So in our use case, in our demonstrator, this adhesive, it will act as a structural adhesive during the production. So the idea is to bond the deck and the hull. At the same time, it may also provide additional benefits in terms of repair, replacement of the bonded components, or more selective disassembly, and improve the end-of-life strategies for composite boats. So that's we are using these adhesives. So now my colleagues allies from CIDETEC will explain everything related to this adhesive in more detail. So that's all from my side.
So to continue with this BioStruct project, within BioStruct project, CIDETEC is developing the bondable bio-based adhesive for marine industry. As Rebecca explained before, this debondable adhesive will be applied to bond the hull and the deck of the boat. These debondable bio-based adhesives are crucial for promoting sustainability and to reduce environmental impacts in industries that really rely heavily on composite materials like shipbuilding. So regarding these debondable adhesives, they are not just a new trend, but they are a necessity for increasing circularity in the industry. What makes these debondable adhesives special is their ability to bond different parts during a normal operation, but also can be triggered to detach on demand after applying different external stimulus, as explained before, Camille. This the bonding on demand property opens the door for efficient repairing and easier recycling at the end of life of different components. With the use of the bondable adhesives, dismantling parts becomes easier and reducing the downtime. And another key benefit of these adhesives is that they allow for rework. So they enable an easier removal of wrongly positioned parts, for example, during the manufacturing process, which is quite interesting. Okay, so the main objective of the project is to develop a new adhesive and a new bonding technology for the assembly and disassembly and repair of composite parts. And to develop this adhesive, we have selected an epoxy adhesive, making it dynamic. And to start with the formulation, Amura defined the specifications that must to fulfill this debondable adhesive. So here you have the specifications of this debondable adhesive. Regarding the curing temperature, it needs to cure at room temperature or maximum at 40 degrees. It needs to have a TG around 70 degrees. We need a fixture time around 4 hours. Regarding the tensile strength, it's quite open between 15 and 50 megapascals. And regarding the presentation, we need a two-component epoxy adhesive, isotropic-like paste. Okay, so for the development of this debondable adhesive, in the BioStruct project, we have developed an epoxy-based adhesive. Why an epoxy-based adhesive? Because it is well known that this epoxy adhesive offers high mechanical and chemical properties. They are highly used for structural applications. They are suitable for joining metal, composite, thermoplastic, glass, or wood substrates. And their curing window spans from room temperature up to 120 degrees approximately. Okay, taking this into account, in BioStruct project, CIDETEC will develop a structural bio-based epoxy adhesive and bonding process based on our patented 3R technology explained before by Arad. In this case, to obtain the bondable adhesive, we will introduce covalent adaptable bonds to these epoxy adhesive networks. These covalent adaptable bonds are special because they are reversible, and we can differentiate between two different covalent adaptable bonds, the dissociative and associative bonds. In dissociative networks, we obtain a cleavage of the bond during the exchange, And in associative networks, we obtain a softening of the material while constant cross-linking density is maintained. The main consequence and the main difference of these two covalent adaptable networks is the distinct viscoelastic behavior during the thermal reprocessing steps. And here in this project, we will introduce aromatic disulfide bonds, which are associative, to obtain an associative-like network. Here in the following video, you can see what occurs within this debondable adhesive layer when we heat the material. As you can see, we don't cross-link the material. What we obtain is an exchange between these disulfide bonds, allowing this easy dismantling of bonded parts. Okay, so regarding the properties of this debondable adhesion, we perform the dynamomechanical analysis. We obtain an adhesive having a TG of around 85 degrees, and as you can see above this, the glass transition temperature, we still obtain a cross-linked material because it's associative. Here we can see that we obtain a plateau of the storage in the storage modulus above this TG. And in order to demonstrate and to characterize these dynamic properties and these reversible properties, we performed stress relaxation tests at different temperatures. For that, we heat the material at different temperatures and we applied a strain of around 1%. And we monitor how the relaxation modulus decreases over time. As the temperature increases, this relaxation is faster, allowing an easier debonding. So this demonstrates that this material is dynamic. And regarding the adhesive properties, we perform a single lab shear test over the substrates manufactured by Amura, and we obtain a lab shear strength of around 8 megapascals at room temperature. And then here we can see that if we heat this adhesive layer up to 150, this shear strength decreases drastically, and we could separate these two substrates with hand, because it has a shear strength lower than 1 megapascal. And in order to demonstrate that we can also rebond these parts, we applied heat and pressure to this specimen, and then we tested again. And we obtained a lab shear strength of around 6 megapascal, which means that we recovered more than 75% of the initial properties. So here you have a summary regarding the specification that we fixed at the beginning of the project regarding the curing temperature, TG, and so on. And here you can see the obtained values that we obtained an adhesive that has a working time higher than 2 hours. The fixture time is around 6 hours. We have a TG of 88 degrees, a lab shear strength of around 9 megapascal, and an adhesive that is debondable at 150 degrees. And here, you can see two videos where we demonstrate this debonding and rebonding capacity. In the first one, you can see that, maybe I will put again. If we hit this specimen and we put some 18 kilograms, we hit the material and we can debond the material. And as you can see here, I don't know, we obtain a more or less cohesive failure of the adhesive. So in the next video, you can see that we repaired this specimen by just applying heat and pressure here, and we tested again the rebonded specimen, and you can see that it's repaired, and we obtain a breakage of the substrate, not of the bondage. So we can say that the developed adhesive is debondable and also rebondable on demand. And to conclude, just as a conclusion of the properties obtained in this BIO-UPTAKE project, we have obtained a debondable and reparable 3-year dynamic bio-based adhesive. This debondable adhesive has a TG of around 85 degrees and a shear strength of around 8 and 9 megapascals. Now we are working in the methodology for easy debonding, and we obtain a repairing efficiency higher than 75%. And this new solution will contribute to reduce maintenance cost of marine composite parts. So this debonding on demand will permit the recycling of the substrates or of the different components at the end of life. So that's all from my side. Thank you.